Thank you very much. We've heard some talks about what happens here on Earth, and now I want to invite you to go with me on a journey to a distant galaxy 2 billion light years from our planet. This is Hercules A. It's a giant elliptical galaxy, and we think there's a black hole at its center that weighs about 4 billion times the mass of our sun. Now, this is what you see in the optical, and it's a beautiful galaxy. It's not amazing. It's not one way or the other. But when you look at it in the radio, you see something very interesting. Imagine putting on radio goggles and seeing blowtorches of light-speed jets coming from the center of this galaxy. What's causing this? The only thing that we can think of that could be causing it is a supermassive black hole spinning. And as matter accretes onto it, energy is then distributed from the north and south pole in these jets. There are 20 billion supernovae worth of energy in those jets. So it's really a monster that's powering this galaxy. If we could zoom in, if we could take a picture of a black hole, we would be able to test Einstein's theory at the black hole boundary, one of the only places where we think it might break down, and look to understand the dynamics of black holes in the centers of these galaxies. And that's what the Event Horizon Telescope is all about. Now, this is the closest that we've come so far to seeing what a black hole actually looks like. This is a simulation in a supercomputer, which puts all the physics that we know of, all of Einstein's equations and Schwarzschild's solutions, and solves them in a dynamical way. And you see this circular feature. That's the last photon orbit. That's the orbit where light has to orbit in a circle around the black hole. And if we could measure that, that would be one of the signposts that Einstein is correct. Now, how does this actually happen? How do you get this dynamical feature? Well, if you trace the pattern of light around a black hole, you'll see that some light from behind the black hole is bent gradually around the black hole. Some does perfect loop-de-loops. But then, if you were to position yourself at a screen distant from the black hole, where we are at Earth, you would see all the light from behind the black hole come around, and at that last photon orbit, form a ring. So imagine that everything inside the black hole has been swallowed by the event horizon, the point where the gravity of the black hole is so intense that even light cannot escape. And the size of this is, as you can tell from Einstein's equations, the square root of 27 times a handful of fundamental constants. Now, this is really interesting. If we could lay a ruler across space-time and measure that, we would have a way to confirm Einstein's theories and even weigh a black hole. The problem is that the nearest supermassive black holes we know of only sub-10, 50 microarc seconds on the sky. That's like seeing an orange on the moon. So no normal telescope can do this. So we use something called very long baseline interferometry. We take radio telescopes around the globe, we point them at the same black hole at the same time, and we record data using atomic clock precision on banks of hard disk drives. We freeze the light, and then we bring it to a central location later where we compare it, called a correlator. And that gives us the effective angular resolution of having a telescope as big as the distance between our dishes. So an optical dish bounces light onto a focus, and all the light arrives there at the same time. We do this in a supercomputer later by sliding the recordings back and forth in time. But only a couple of telescopes is not enough. We would only have a few small silver bits in this virtual mirror the size of the Earth. And to see this black hole, you need a telescope as large as the Earth if you're going to see it in the radio spectrum. So thankfully, the Earth rotates. So during the course of an evening, while we're observing this black hole, the Earth itself moves our observatory around. We weave, just as a spider might weave reflective silk, a web of this dish. And after one whole revolution of the Earth, as you see here, we filled in enough of the aperture, shown here on the right, to make our image. So this is called Earth rotation aperture synthesis. We let the ground moving underneath our feet do all the hard work for us. So now we have a telescope that's as large as the Earth, but now we need to build out the full array. We have to not just use one or two telescopes, but many. Now, in the late 2000s, a small team measured the size of 2 black holes, and we saw that there was the possibility of imaging a black hole for the first time, because we saw the size was just the right size that was commensurate with that of the shadow. But we had to build out the whole array. So we added telescopes in Arizona, in Mexico, in Chile, in the South Pole, in Spain. So everywhere you see here. And we went to telescopes that normally did not do this kind of work. I can't stress that enough. We had to go to directors of telescopes and say, we want to bring atomic clocks to your observatory. We want to bring bespoke electronic equipment. We kind of want to take over. And they said yes. So it was really a political coup to get this done. Now, we trained all of our telescopes on this source here, Virgo A, or M87, which is 55 million light years away. And we didn't know what exactly the mass of the black hole was at its interior, and it's located in the point in the lower left there. And we needed to zoom in on this photograph by a factor of 100,000. And we were hoping to see this ring, this last photon orbit. And when we digested the data, this is what we found. This is the first image of a black hole ever made. Now, this is a treasure trove of scientific result. Like, first of all, it's rare to have a prediction so cleanly seen in nature. So nature was somewhat kind to us to give us the right orientation and the mass so that the Earth-sized telescope could just perceive the dimensions of this black hole. But more than that, you'll see the bottom is brighter than the top, and that's because the gas is coming towards you on the bottom. It's Doppler boosted and it's brighter. So think of a train whistle getting higher in pitch when it's coming towards you. And then on the top is moving away from you, so it's getting dimmer, just as a train whistle gets lower in pitch. This is the first time we're seeing relativistic motion, light speed motion around the black hole, and this lets us understand the spin of the black hole. And we used it also to weigh the black hole. Because we now know the size of that ring and the distance to this galaxy, 55 million light years, we've weighed the black hole, and it is about 6.5 billion solar masses. But more than that, we now have a window in which we can study black holes. We can go back to this black hole year after year after year and sharpen our images to really understand how we can make better tests of Einstein and understand the physics of matter accretion onto the black hole, to understand how the black hole launches those jets that I showed you before. Now, to do this, we had to get creative, and we created tension within our collaboration, a creative tension. So we didn't rely on one data processing stream, we had 3. We didn't rely on one imaging algorithm, we had 3. And we even split everybody up into 4 separate teams that had no contact with each other. And I'm really glad we did that. And why did we do that? Because it's really hard to tell the difference between fried chicken and labradoodles. Okay? I'm using this to make a point. We had no idea what we were going to see. And we didn't want to be fooled by what we thought we might see. So we had to split everyone up. And this way we had complete independence. And when we all came together and saw the same thing, then we knew that we were on the right track. And if you think that's bad, try chihuahuas and blueberry muffins. But the important thing here was not that chihuahuas looked like blueberry muffins, but that we were honoring a 100-year tradition that reaches back to Einstein and Schwarzschild. When you are studying equations that they wrote down that are as alive today as they were before, you don't want to get it wrong. They were literally looking over our shoulder. And when Einstein is looking over your shoulder and Schwarzschild is looking over your shoulder, you don't want to mess up. Now, where are we going from here? We have a project that we've just launched called the Next Generation EHT. I told you we used telescopes in different locations, but they already existed. We had to go where those telescopes already were. But now we can play this interesting optimization game, perhaps using quantum computers, where we can put the telescopes anywhere we want. So now we want to double the number of antennas, fill in a tailored way all the holes in this Earth-sized virtual lens to increase our imaging fidelity, because the next thing to do is to make movies. So we can do this by adding all those dishes that I just showed you, where all the blue traces were the new connections, or we can use space-based telescopes. So on the left, you see how fast we build up that virtual Earth-sized array when the Earth is rotating. On the right, you see the effect of having 4 orbiting satellites all moving around the Earth, and you fill in that virtual lens, seen all the way on the right, almost perfectly. Now you can take snapshot images every minute, every 2 minutes, stitch them together to make a real-time movie of what's happening in the supermassive black hole in the center of our own galaxy. And the reason that's important is because the one in the center of the Milky Way weighs 1,000 times less than the one in the core of Virgo A, so it evolves 1,000 times faster. We need to make a movie, otherwise it's like taking the lens cap off your film while somebody runs by. It'll just be blurry. So we need to make movies to really understand black holes. That's the next step. And if we can do that, then we would wind up seeing something on the screen here. So on the left-hand side, you see a model that comes from a supercomputer. On the right-hand side, you see what we think we can probably reproduce if we have the whole Earth array, a couple of antennas in low Earth orbit, and then even one in geostationary orbit, which is about 5 or 6 Earth radii away. If we had all of this, we can deliver real-time movies. Now, 10 years ago, we wrote a paper and we said, we think we're going to make an image within 10 years. And we made it by 2 months. Okay, in 2009, we wrote that paper, and in 2019, we actually did it. And I'm going to make a prediction that we can make movies in the next decade. Don't hold me to it, but I like our chances. Now, the key to this really was the collaboration. We started small, as I said, and as the saying goes, if you want to go fast, go alone, but if you want to go far, you go together. So we needed to bring expertise from all across the globe. We bypassed borders. We nimbly sidestepped the things that divide us usually as people, politics and things like this. We brought the best ideas we could to the table. We're now 200 people strong, 60 institutes working in 20 countries and regions, and this is really what made the entire project run. Now, what was the impact on humanity? Well, it's nice to get a Google animation. Okay, who doesn't want to get a Google animation? And this happened the day after our discovery. But what really rocked us on our heels was this. This was featured on the front page of every major newspaper in the world. So we came down from our hotel rooms on April 11th, and when we saw the Washington Post, the New York Times, the Wall Street Journal, just in DC where we were rocked back on our heels. And when we saw everything everywhere in the world, we really got excited. This is really a teaching moment for us, but also for everyone here. We really do see ourselves as explorers. We went on a voyage of the mind, 55 million light years away. It doesn't mean anything unless we come back and report what we found. So we broke down a number of barriers. Walls fell to make this happen. There were walls of time. We feel very connected to Einstein, Schwarzschild, all the luminaries that came before us, and most recently Stephen Hawking. And we used the scientific method. We honored the traditions of rigorous scientific analysis. We didn't accept what we saw. We really needed to test it in every way possible. We honored them, and we broke the barrier of time. We also broke the barrier of borders. We just sidestepped any kind of politics, any kind of border that we saw, and we reached out to all the groups that we needed to make this a reality. And we also broke down political barriers. We went to these telescopes, and we convinced them that this was the thing to do. So this really does give us hope that a lot of things can happen. Now, the science historian Peter Gallison reminds us that some images are iconic. Some things just get burned into your brain, like this one. This is the first X-ray made by Röntgen in 1895. For the first time, we saw something that we thought was invisible, that we thought maybe was impossible. It was a little terrifying, but it gave us new perspective on what we could do and regions of the universe that were now accessible to us. Here's another one, Earthrise over the moon. This is sometimes called the best environmental preservation shot ever taken because it makes us feel vulnerable. Again, it gave us a new perspective on things. And I think that this photo is destined to become iconic in that same way because it gives us perspective. It certainly has inspired us. It's given us perspective on what's possible and what is scientifically doable. And we hope it has inspired you too. Thank you.